Oh, hey, Jane, what are you up to?
Oh, nothing much. I'm just pulling this object up this frictionless incline.
Classic. Let me check it out. Is there anything I can do to help, Jane?
Well, I guess you could show me some math.
First, imagine the binder is this right triangle. We will define this angle as theta, and this angle as x. Now here's the gum, resting on the frictionless incline. It has a weight of 50 newtons. Now imagine this is a coordinate plane. This is the x, and this is the y. So here we have three separate triangles, all with one angle of 90 degrees. By definition, the three angles of a triangle must add up to 180. So we know 90 degrees minus theta is equal to angle x, and vice versa. We can also define this angle as 90 degrees and subtract x from it. This proves that the two angles labeled theta are congruent as they both have the same relation to angle x. Now that has been established, let's move to the weight. In this case, being created by the gum's gravitational pull. If we look at this coordinate plane, we can see that the x component of the weight will be parallel to our incline and the y component will be perpendicular. You can solve the components using sine and cosine, but since the coordinate plane is this way, it will be reversed. We use the gum's weight of 50 newtons to derive the two by taking 50 sine theta to solve for the x component and 50 cosine theta for the y component. I know that's a little confusing, so I'll give you an example. Let's imagine theta is equal to 20 degrees. With this extra info, we can now plug in the 20 to our equation to solve for the x and y components. Through this, we find that x is equal to 17.101. Why is this relevant, you might ask? This tells us how great a force we need to apply in order to pull the gum up the frictionless incline. Now, Jane, I know you can pull with a force of 40 newtons.
Can I?
Yes, you can. I know you can. We just need to figure out the steepest angled incline you could pull.
Okay, you got it?
No.
Alright, well I have one last trick up my sleeve.
Where is she?
Sorry I'm late. I had to change my outfit.
So did I.
Crazy!
Oh my god. Wait.
Yeah. Okay, so here we have this block, and everyone knows that gravity pulls things straight down towards the center of the Earth. But in this case, thinking about straight down and straight up isn't super helpful for us because we're mostly concerned with whether the block is going to go down the ramp or up the ramp. And so to break it into those components, we take this weight and we say, well, that's the same as if we went straight down into the ramp this amount and straight along the ramp this amount. The amount that's straight along the ramp is the amount that gravity is trying to pull this block straight down the ramp. And so if we know that it's not moving and there are no other forces, then this F pull going up the ramp must be the same as this in magnitude because it's not accelerating. So then this we know is mg sine theta because this weight vector here has a magnitude of mg and this angle is theta, which is the same as here. And so this opposite side is the sine of theta is opposite over hypotenuse, and so when you solve that you get that this side is mg times sine theta.
Wow, that was great! Now you finally understand math.
I know, right? Slavinsky is so helpful.
I know, right?
The largest value for theta for which I could pull this 50 Newton box of Eclipse gum with a pull force of 40 newtons up a frictionless incline would be 53.13 degrees.
Guess what?
What?
We just learned some math!
That's great! Is that enough?
Yeah.